Hi everyone, welcome to my video series. In this video I'm going to talk about waves and the properties of waves. Usually in the classroom I do a ton of demos regarding waves. Unfortunately I don't have the ability to do it. I tried to video some of them but they just didn't really come out that good and I need some of my supplies, so I apologize. Usually I'm a lot more interactive, but I'll make the best of what we can and show you a lot about waves. So what I'm going to do in this video lecture is talk about some properties of waves, their anatomy, some of their characteristics. We're going to be able to measure some features of waves such as amplitude and wavelength. We're going to do some timing features of frequency and period. And then at the end of the slides we'll talk about wave speed and what changes the speeds of waves and how does it affect the wave speed, how medium affects wave speed. So as we go through, here we go. Like I said, we'll talk about all different types of waves and models for our waves and do some calculations. So waves is a very important topic. So besides the very physical nature of a wave, you know, if you look at some of these, you can see this pattern of moving up and down, or like ocean waves. I like to put the ocean wave down here. You know, when you think of waves, usually I go right to ocean waves. But they're very important for communication. So in other words, you know, we use waves to see. You know that. You probably don't really think about it, but we use light waves to understand our environment, right? The light comes from other objects, goes into our eyes, and we interpret it as whatever thing it is. We interpret color, we interpret intensity, and that tells us all about our world, you know, what's in front of us, what's far away, what's close up, what color things are. It's all very important features to understand our world. The other feature is sound waves, right? So same thing. Of course, one of our main things we use sound for is communication by literally talking to other people. But of course, there's so many other forms of sound, right? So we can play instruments, we can sing, we recognize sounds and tones. I know a lot of people say they're tone deaf and they don't know how to sing or songs, but you do. For example, you know you actually know the voice of your mom or your you know, your friend or your brother or sister, parents. It doesn't matter who, you know, if someone that you know for a while, you know their voice, so you have some tone quality and the ability to figure out tone. So sound waves are of course very important. We also use it to understand our environment, right? Just based on how something sounds, you can tell if it's a big room or a small room, if someone's close or far away. These are all features that you use in terms of waves. So understanding waves is just huge. Excuse me, another very big important thing we use waves all the time is for communication. So cell phones, so we take the information and we, quote, digitize it, not quote, we literally digitize it so that it travels across, you know, wherever we need to go wirelessly, which is crazy, right? And then we decode it into other things. So waves are incredibly important, and we use them so often that we don't even recognize it. So you can see a bunch of things happening on this screen here. This is the waves of instruments, of colors. You can tell the difference, what happens to the wave when you change the color, of sound waves. Although we're not going to talk about polarization because light can actually go in different directions. Oh, excuse me. Polarization basically takes those waves and makes them into one direction. That's polarized, just like your sunglasses. Your sunglasses are polarized, and if you have actual polarizing sunglasses, they look kind of weird. I do, which is kind of fun. But anyway, moving on. Let's start with the basic definition of a wave. So a wave is a disturbance that travels through a medium without any transport of matter. So that's a hefty definition, right? So basically what it means is that if I have some sort of particle, that the particle moves momentarily and it doesn't go down the length of, you know, your string right here. And the thing that we see traveling is the energy of the wave, not the displacement of the wave itself. So actually I have two demonstrations I could show you to kind of understand this. I'm going to read the definition again so you can have that in mind when I show you the demonstrations, but a wave is a disturbance that travels without any transport of matter. I think my favorite example is actually doing the stadium wave. So let me just get out of this PowerPoint so I can show you this. go over here. And I know this is silly, but if you... Okay, I'm going to put that there. All right, I know this is silly, and I'm going to sit back to do this. But if you think about a stadium wave, right, I'm sure most of you are familiar. What do, right? You sit down, you stand up, and then you come back down, just like that, right? You don't actually go 3 seats over, right? You don't, like, leave, right, when you do a stadium wave. That's what I mean about transport of matter. That you come up, a disturbance, this is the disturbance, you come back down. And you don't actually go down the whole audience, right, in the stadium. That's what I mean by disturbance of matter. So let's go ahead and just quickly look at this for funsies. There we go. But there you go. There's a wave, right? You can see the wave in the crowd. The crowd stands up and sits back down. It's a really good wave. There we go. It's the world's fastest wave, everybody. How exciting. Anyway, you get my point, hopefully, with that. Let me show you another really good example. I think all of you are loving PhET by now. Maybe, maybe not. Oops, no, I don't want that one. I want this one. So one thing that's really helpful, I'm going to go to sound specifically. So, you know, I'm going to let the speaker create a wave, right? So what I'm going to do is the particle mode. Watch this, is really cool. Boom. So sound is, you know, basically for the most cases, sound is a disturbance amongst the air particles. But I love this simulation because notice that you have these red dots, right? Notice that that red dot in the middle, right on my mouse right there, moves back and forth. I'm not saying it doesn't move, but it doesn't move across the screen. Isn't that crazy? To this day, even though I teach this, it's still just, it boggles my mind. So it means when I talk to you, the particles in front of my mouth don't actually go to the other person, okay? They move momentarily, and then it sets off the next set of particles, and then the next set of particles. And that's what you see, the disturbance. You see the disturbance of matter. Now, because it's in a periodic way, you see these patterns, which we call waves. I'll talk more about the wave and how we can change the features of the wave in one moment. So I'll leave this here, actually. So now what I'm going to do, so yes, let me just stop really quick right here. So a wave transports energy. Transports energy. That's what you're seeing. You're seeing that wave that you see is energy. You don't see matter being transported, okay? Now matter does move, careful, but it doesn't go across. So hopefully you understand that, and if you don't, just let me know, because it is kind of confusing, because I say it doesn't move, and then it does move, and then you're like, what are you talking about? So we'll come back to that. So I have a plethora of wave terms and things to discuss. So we call one disturbance a pulse. So you can see here, that's literally exactly what you think it is. I take the wave and I create one disturbance. So you're seeing a single disturbance right there as a pulse. And then usually a continuous disturbance is exactly what you've been seeing before. Oh, excuse me, I don't know why I'm so tired. In terms of that other simulation, right? So the simulation that I showed you, we go back to it, just like that. That's a continuous wave. I can send a pulse. There we go, ready? I'm gonna let this kind of even out. I'm gonna crank up this amplitude for a quick second. Pulse. There it is, one wave. Versus the continuous wave, right? I'm gonna actually lower the amplitude just a tad. Up the frequency. But anyway, you get the idea. I didn't know you can pulse. Fun fact. That's cool. I could pulse a light. Let's pulse a light. Boom. There you go. Boom. Let's make a red light. Boom. Okay, now I'm just having fun. That's a pulse versus a continuous wave, right? I think you obviously can pick up the difference. Okay, so there's two types of waves based on how you make the wave. This is based on how you make the disturbance. This is based on disturbance. I said it a couple times. Did that on purpose. There's a longitudinal wave and a transverse wave. And the longitudinal wave travels along the medium, exactly as it sounds. So I do this as a classroom demonstration, so you're going to have to kind of use your imagination. If I had a slinky and I stretched it out, and I wanted to make a longitudinal wave, I would take that slinky and I would push it along the slinky. So literally push it this way or pull it that way. So notice the arrows right there. That makes a disturbance. It makes a pretty cool wave when you see it on the slinky. And what you'll see is there's areas of the slinky that get really squished together and really far apart. So those are the waves that you have here. The disturbance is in the same motion. A longitudinal wave goes along the wave. That's kind of how I remember it. Some physical examples. So sound wave works like this. So sound actually takes the particles and squishes them together. Just like that. And earthquakes work this way. The earthquakes can compress and do that. Now there are some other waves called transverse waves with earthquakes, but that's just another example. A transverse wave. So the transverse wave is if you do what you normally think you would do to make a wave, you would wiggle something right back and forth. Well, another important feature, let me get my pen out since I have it ready to go. Actually lying, I don't. We're going to get it ready to go. Let's get it ready to go. Is that, again, I'm talking about the wave disturbance, how I disturb the wave. But in both of these cases, the wave, I'm going to do it in blue, the wave travels this way, right? So in other words, the wave will go along this way. And same thing over here, the wave travels this way. But in the red is the disturbance, right? So I will wiggle my hand up and down for this disturbance. And for this disturbance, I'll wiggle forward and backwards. So notice, right? This is the longitudinal, which goes along the wave. The transverse is perpendicular to the propagation of the wave. So how the wave is moving, propagation. So notice the difference, right? Transverse. Now, I could do transverse like coming in and out of the page too. That's another way. But just to show you that distinction. Now, light waves work this way, and ocean waves. Again, there's some. I'm simplifying ocean waves. You can have some longitudinal effects, but again, we're going to simplify it. Two other types of wave. This is based on medium, not disturbance. There's a mechanical wave and electromagnetic wave. Those are two different types of waves. So, with the mechanical wave, what you're doing is you're moving matter, which is pretty much everything. Anything that you physically move. So a slinky, water, sound, all those are mechanical waves because you physically move matter. Now, when it comes to electromagnetic waves, those are different. So electromagnetic waves are created by oscillating charges. And the weird thing is it doesn't need a medium. So like I explained in the beginning of this whole unit, if you took a charge and you started waving it back and forth, that's an electromagnetic wave. Now the interesting thing is it doesn't need a medium. In other words, it could travel through space. Cool, right? I mean, it's important because without it, we wouldn't have the warmth from the sun, if you think about it, right? So the sun creates lots of energy and radiates that energy in the form of all different spectra, but mostly in the visible light range. And that light actually gets to us at a perfect temperature. We're in the Goldilocks zone when it comes down to planetary distance, which means it's just right. So it's at the just right distance for us to be comfortable. But sound, there's no sound in space. In fact, if there's a giant explosion, stars explode all the time, but we never hear them, right? I mean, they're also very far away. I mean, you can argue that, yes. But ultimately, any explosion in space wouldn't make a sound. So if our sun were to disappear, we wouldn't, if it exploded, we wouldn't hear it, number one. It actually, fun fact, we wouldn't know for 8 minutes because it takes 8 minutes for that light to get to us. So weird, right? Crazy stuff. It's all crazy stuff. Okay, regardless of the type of wave, whether it's electromagnetic or mechanical, it doesn't matter. They all have similar features, which we can model with this diagram right here. And this diagram has specific labels. So the tops are usually called crests. Think of wave crests. And the bottoms are called troughs. So I have 3 crests and 3 troughs in this case because it's symmetric. That's not always the case. And so the heights of these are the same, again being symmetric, meaning it doesn't have to always be that way. The height of this measured from this center line is called the amplitude. So how much you disturb it, right? So a little amplitude, I mean I'm going to show you this later, but just since we're talking about it, a little amplitude would look like this, right? A little disturbance versus a giant disturbance. So that's what the amplitude measures. We're going to always treat the amplitude on both sides as the same size. So this and this are equal, like that. But that's not always true. You have this effect called dampening. So you have something that might do this, and it's losing energy over time. That's called dampening. We are not going to do that. All right, coming back to our PowerPoint. So what I'm showing you is the size of the wave, called the wavelength. Now, I did pick a really weird spot to show you this, but most importantly is the size of your wave. Now, if I were to trace this out, the size of my wave, it would start here and go down and come back up. Now, a lot of people stop here, but that's wrong because a full wave includes the down and the up, okay? So the down and the up is a full wavelength. Notice that if I were to start going again, I would repeat myself, right? I would start making the same shape. So once I start repeating myself, I stop. This is, by definition, what we call wavelength, which is the symbol lambda, so upside down y. Now, like I said, I picked a weird spot for it, but honestly, you can measure it from anywhere. In fact, my favorite spot to measure it is actually from the top of a peak, because I think it's easier just to look across like that. Remember, the wave has to go all the way down. It's not done here, because it has to go all the way back up. This is the size of my wave, the wavelength. So I can have a big wavelength relative, so if I look from here to here, I can have a teeny tiny wavelength, right? This is a small wavelength. I can't even physically get in there. That would be the wavelength, right? Like that. So this is the wave size, how big your wave is. So for example, those gamma rays are very teeny tiny like this, and those radio waves are very big. So that's the difference between wave size. And then usually we call the middle point the equilibrium position. There's all different names for this, just know that. So sometimes you might read on something like else, but no, more or less what we're doing is we're cutting the wave in half to make it symmetric. So that's the middle of the wave. And this line is important for measuring amplitude. It's not necessarily important for measuring wavelength. So again, this is just a diagram of exactly what I just talked about. Maybe you like this better. And this is the descriptions that I just said in words. So as always, it's fun to stop that video. In class, I would have you stop and do this. And here are my questions, right? First question, how many wavelengths are in here? And what's the amplitude of this wave? So why don't you take a quick second and stop and answer these 2 questions and see what you think. Pause the video for a second. Okay, I assumed you at least tried to pause the video and try to answer these 2 questions. A little check for you, right? So I'm going to go ahead and just shout the answers out first and then explain them. So how many wavelengths are here? There are 2 wavelengths, and the amplitude is 5 centimeters. So you can check your answers. So how do we know there's 2 wavelengths? So I will start here, and I'll trace out 1 wavelength, so the full up and the full down. So notice that basically this shape right here is equal to one wavelength, right? That's equal to one wavelength. And notice that I have another one of those shapes. I have 1, 2 wavelengths here. So you can kind of memorize that. Counting peaks is not helpful in this case if you notice, because then I have 3/4 and 1/4. I mean, you can do it, but it's not helpful in this situation. So there's two wavelengths shown, and then the amplitude is measured from the middle line up. Since it's conveniently 0 to 5, it's 5. I could also measure it from here to here too. The -5 just means it's below, so the magnitude of it is still 5, meaning notice the value if I ignore the sign. So these two are both correct answers. You can honestly ignore the negative sign in most cases, because I just care about the size of it, not the direction. But if you did put negative, it's not wrong. So we're going to talk about wave timing features. So because waves are periodic, in other words, they repeat themselves, we can measure those periods, literally, how many times they repeat themselves. How long does it take to make one of those cycles? So we measure that in seconds, and if you notice, that's exactly what it means. How long does it take to make a wave? So if we have time on the axis here, it's very important. It's not position. Without time, we won't know it. But how long it takes to make one full wave. So we're back at that idea, right? So the time it takes to start here, make a full wave up and down, it's how long it takes to make that. That's the period. I make one wave in 50 seconds. That's what this means. So if the period is 50 seconds, I make one wave in 50 seconds. My period is 0.5 seconds. That means I make one wave every 0.5 seconds. It's kind of like a per kind of thing. All right, I'm actually going to get rid of this for a moment. Frequency is a little different, but related. Frequency is how often do you make a wave. So instead of counting and measuring time, you're going to count how many waves are made in a certain amount of time. Frequency is measured in hertz. I think we've done this before in our class. But translated to waves, it's how many waves you make per second. So if I say 50 hertz, I made 50 waves in 1 second. That's a lot. Can you count to 50 in 1 second? I don't think so. So if you think about that, it's a pretty fast measurement. To show you some features here, so high frequency means there's a lot more waves happening, right? I'm going to go ahead and count these because that's fun to do. So if you look here, let's do this. I have 1, 2, 3, 4, 5. I have 6 waves. Now, I'm going to pretend it's per 1 second. It doesn't actually tell me the time, but we're pretty okay with that. Notice that this is 1, 2, 3 waves per second. That's a second one. Oh, that looks terrible. It looks like 15. 1 second. Okay, so if you notice, essentially what's happening here is that this one has a higher frequency because you make more waves per the same amount of time. Frequency is related to period in the inverse. Fun. What do I mean by that? Notice that this was a small frequency, but this actually has a bigger period, right? Period is the time it takes to make one full wave. And notice that this is much bigger here than it is over here. This one we had a big frequency, but we had a low period, right? The period is much smaller. So you have an inverse relationship between period and frequency. Frequency and period are inversely related. So another inverse relationship, I'm going to use this diagram because it's helpful, is wavelength. Wavelength is inversely proportional to frequency. Very interesting point. So notice that's true too. If a wavelength, remember wavelength is this size. It's actually the same measurement but in meters of the period, right? If you notice, versus this one. So this is wavelength right here. In this case, the wavelength is small, but the frequency is high. And notice here, the wavelength is big, but the frequency is small. Frequency to wavelength is an inverse relation. So that's another feature that's important. It will come up on many things, homework, your quiz, all that fun stuff. Well, here we go. Another great way to check your work. So again, I'm going to pause this video. I want you to try this out and see what you get with this. So I'm going to go ahead and pause awkwardly for a few seconds, assuming that you're going to do this, and then I'll start again. Okay. I hoped you paused the video and you took some time to do this. What is the amplitude for each vibration? So in this case, for A, the amplitude is 5. I'm looking from the middle line and going up to here. And that's measuring 5 units. In this case, it's degrees. So same thing. I'm going to start from the middle unit, from the 0, and go all the way up. This is measuring 100. So that's the amplitude here, A for amplitude. That's our symbol for amplitude. How convenient, right? What's the period of each? Okay, it's the period. I have to figure out a full cycle. It actually doesn't matter where I start for this. Actually, I'm going to clear the screen just so I can have a clean screen. But in this case, it's helpful to start the 0 because then I go from 0 to whatever time. So one full wave is from here to here. The period of wave A is 1 second. Now notice I could have started here and do the same thing. But notice I would have to do 3 minus 2, right? Because I want the time of this section, not the whole time. So this does work no matter where you measure from. But like I said, it's easier to start from the 0 for this case. Same thing. I start from here, go all the way till I make a wave again. The period for this is 2 seconds. So for B, it is 2 seconds. Okay. I hope those went over well. And if you have questions, just let me know. So I'm just seeing where I'm going with all this. Fun fact. Okay, so if you don't have a graph, this might be more useful for you. So notice they're weird, right? They're really more of a definition than an equation, so that's why they kind of read like a definition. But frequency you calculate by doing number of cycles divided by time, and period is the time it takes to make a cycle divided by your cycles. So, hope you got that. Let's calculate both. Frequency is going to be the number of cycles divided by period. So 42 cycles is the number of cycles divided by a time it takes to make those cycles, 6 seconds. This will be 7 hertz. Now, if you're wondering why this is hertz, the definition of a hertz is an inverse second. 1 over seconds is by definition a hertz. Cycles is not a unit, it's just a count, right? I'm counting how many cycles. So we put a 1 as a placeholder for that. And then notice time is in seconds. So this becomes period. Becomes hertz. I was thinking period, I was thinking ahead. Period is the time it takes, so 6 seconds over the number of cycles, 42 cycles. With that, I do need a calculator for 6 divided by 42 gives me a period of 0.142 seconds. Okay, so that's how you use these equations. These translate to the following. 7 hertz means that I make 7 cycles per 1 second. So it's pretty fast, depending on what it is. And then this translates to, it takes 0.142 seconds, so like a fraction of a second to make 1 cycle. And then I hope that makes sense. And notice that these are related, right? In order to make 1 full cycle, or in order to make 7 cycles in 1 second, they have to be less than a second. In fact, they're literally divided by that. So, if you notice, they're actually inversely related, like I talked about. Actually, I'm going to go back really quick. Notice that these are literally the opposite of one another, right? If they're flipped. So you can use another trick, which we did talk about with the centripetal force, like this. So if I want to find the period, I can find the frequency. So I'm actually going to use the numbers from before. So we said frequency was 7 hertz, right? Instead of doing what I did before, which was what, 6 seconds divided by 42 cycles, we got 0.142 or something like that hertz, right? I can do period is 1 over frequency. So that means I could do 1 over 7 and still get the same answer. Oh my goodness, I got the same answer. What do you know? Seconds. I am so sorry. Both of those should be in seconds. I just noticed my error. There we go. That's better. Seconds for period. Look, they're the same. So this confuses people because now you have 2 ways to solve these, right? Of course, it's totally confusing, and I totally get it. So what happens is that this definition is useful for questions like the ones that I just showed you right here, when you have cycles and time. This is good for questions like 1 and 2, right? Notice that 1 and 2 just gives you one number. So what's the period of a 20 hertz frequency, right? This is where this is helpful. 20 inverse. 0.05 seconds. And then I could do the same thing for question 2. Which becomes 0.005 seconds, like that, etc. So notice you could do it with frequency. I'm doing these kind of quick, I hope that's okay. Just gonna do one of these and then screenshot it so I can do frequency. Same thing. Frequency, I could do 1 over period, 1 over 10 gives me 0.1 hertz. And then the second one, 1 over period, 1.03. I'd have you do these in class with me. So let's pretend that you are 3.33 seconds. Okay, hopefully those sit with you comfortably. You'll see a mix of these on your homework. So just know there are better times to use each of these, okay? To be redundant, if you have one number, use these equations. Have one number, use these equations. And then if you have 2 numbers, use these equations. I give you a peace sign, peace 2 equations. Okay. Now you can try, right? These are great questions, hint, 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 that you may see on some things called assessments, maybe some quiz, maybe an exam, I don't know. Just saying, you look really good. But why don't you take a take a couple minutes and try to solve these out. We're almost done, I promise, with this lecture. But maybe to pause, go get a drink of water or something to snack on, and then come try these out, and then we'll finish the lesson, okay? So take a pause. Okay, awkward pause over. I feel so silly doing that, but you know, trying to do what I can. It's so funny. I watch a couple TV shows on the internet that usually have audiences, right? And they don't, and they say like things like, "Oh yeah, I'll wait for your applause." And they wait, and I'm like, "Oh my gosh, I get it." Not that I expect applause. That's not what I mean, but just like how like there's no reaction, right? I'm just kind of talking to a screen. It's a lot of fun. You should try it. Anyway, sorry, I try to be human when I do my lessons, you know. It's not all just me talking content that, you know, there's a person here. Okay, so let's do these. You're probably like, okay, shut up and start working. All right, so let's do it. All right, let's see. I have 10 seconds to make 2 cycles, right? How long does it take to make 1 cycle? Well, good thing I got this number of cycles divided by time. This calculates the period, how long it takes to make 1 cycle. This is, by definition, a period. Don't let it throw you off. You could do this in your head. Maybe, sorry. 2 cycles divided by 10. No. This is what happened, sorry. Big mistake. This is not a mistake. This is a mistake. It should be time over cycle. Sorry, that's what happens when I'm talking too much. Getting silly now. I'm just being silly. There you go. This is still the definition of a period. This is the right way to calculate this. I was right. I was like, you can do this in your head. You can't do this in your head. 10 seconds divided by 2 cycles will give you a total of 5 seconds for the period. In fact, this question is redundant because the period is also, this is the period, so it's 5 seconds. So don't let questions get to you. Sometimes they're repetitive, they are that way. So this is the period. The frequency, you can do this 2 ways. I choose to do it this way because I have 1 number. You could do it by the definition way, it still works out. I believe this is 0.2, but I'm not going to trust my math. It is 0.2 hertz. Like that. So that's question 1. Question 2, uh-oh, we got it in minutes. Take a wild guess what we need to do. You're right. We got to convert this into seconds. So 3 minutes times 60 seconds per minute gives me 180 seconds. So I actually have to do that first, and then we have our vibrations, right? Vibrations, cycles, waves, it doesn't matter what word they use when it comes down to this. How many vibrations does it make in 1 minute? Okay, well, since it specifically said minutes, then I'm going to go ahead and do 360 vibrations divided by 3 minutes for this case, which makes what? Um, 120 vibrations per minute. That's question A. How many does it make per second? 360 vibrations divided by 180 seconds. I think it's 3, but we're gonna check that. Nope, it's 2. Hold on. I think I'm okay. Vibrations per second. Yeah, in 1 second. Yeah. Okay, sorry, I got all confused. Okay, so 360 vibrations per 180 seconds, so you get 2. Okay, that's good. Okay, what is the period in seconds? So, period is going to be the time. So that's going to be 180 seconds divided by 360. So we have 0.5. So it takes me a half a second to make one period, which makes, that's good. It's better with me that it takes, it makes 2 vibrations in that time. Okay. And then the frequency is going to be the opposite, 360 over 180, which gives you 2 hertz. Okay. Again, I hope those sat well with you. And if you have any questions on those, just let me know. Okay. Okay, come on. Come on, computer. What are we doing? Okay, last part of today's lecture is the speed of waves. The speed of waves are constant through the medium. What does that mean? It means all sound waves, as long as you're in, the same room as somebody else, are all going to travel to you the same way. Yelling doesn't make sound travel faster. Talking softly doesn't make sound travel faster. Using a high pitch does not make sound travel faster. Or a low pitch does not make a sound wave travel faster. It all has to do with what the wave is traveling in. That is the medium. What is it made out of? Can you change the speed of sound? Sure. You can increase the temperature of air. That will change the medium. You can change the air to helium instead of air. Or that's what happens when you I'm sure you've heard somebody do this or done it before. Where you don't do it, by the way. Disclaimer, do not do this. But if you suck in helium, right, your voice changes. It's a high-pitched sound. That's because helium is much lighter than air, so it goes out much quicker. The speed changes. There's another thing called sulfahexafluoride. It makes your voice look really low like this. That's because it's heavier as it goes through your voice, meaning the speed of sound is much less. Yeah, and you guys are probably like, this is a crazy person. But the point is true, though. You change what the air is made out of, it changes the speed of sound. So you can't change it by being louder, the amplitude, by the pitch, which is related to frequency and wavelength, or the type of wave. Very important though, electromagnetic waves are actually constant no matter what you do to it, even in the medium that you're in. So it's I'm not going to talk about this, but a disclaimer for physics and anybody who's nitpicking me. Yes, the speed of light really is constant through any medium. It's really crazy stuff, but it works on a different mechanism. We're not going to go into it. So we're going to talk about this. So typically the speed of sound is about 340 meters per second, or about 800 miles per hour. So it's a little fast, right? And of course that changes. So like, for example, if you're playing baseball on a spring day where it's cold and you hear the crack of that bat, the sound wave will be different if you go on a summer day when it's like really hot out and you hear the crack of the bat. That sound wave is going to go faster in the hot versus the cold. Will you notice a difference? Absolutely not. There's no way. But is it there? Yes, it is there. Another fun fact is the speed of sound in water. So I always like to tell this story in class because it's so crazy. Because when I was younger, me and my sister used to play in our grandma's in-ground pool, and it was a ton of fun. And there was this thing we used to do, and we used to go in the bottom of the pool, and we would say like 1, 2, 3, and she would go in the deep end, and I would go in the shallow end, and we would scream at each other. Now we were kids, so it's pretty fun to do it. But the weird thing about it is, despite her being so far away, she sounded like she was right next to me. Well, that's because the speed of sound travels faster in water. So even though she was, 30, 40, 50, I don't know, 60 feet away from me, she sounded like she was next to me because the sound wave got really close. So remember, you interpret sound waves. You can tell somebody's close or far away just based on how something sounds. So it's a weird effect. For homework, you should, over the summer, when you go underwater, if you're swimming, have somebody talk to you or bang something underwater. It's really like trippy, like to hear that. Or like in the ocean, I like to go to the ocean, and especially if it's rocky and you're in the waves, and I like to go like in the waves, you can actually hear the rocks rolling, and they sound like they're next to you, even though they may be far away. It's really just this crazy sensation. So speed of water's the sound travels faster in speed of water. And then imagine if you went to a concert or went to see a show and like the waves didn't travel the same speed, right? Then the guitar would get to your ears, then the drums, then the singing. That'd be weird. It gets to you all at once. Crazy, right? Crazy stuff. Now, I have to be very careful with this because the speed of sound does change in so many different ways and mechanisms that it's hard to really say that this is a definitive way to change the speed of sound. But holistically, if we generalize, generally gases travel faster. Solids travel faster than gases. You can see the numbers here. But there are some exceptions to the rules, and it's based on their elasticity, their temperature. All these things can change things. So even though we have like water as 1400, you can see that rubber, something solid, is not too far away from it. Well, if you think about rubber, it has to do with elasticity. Something that's super compressed is diamond, right? So diamond travels really fast because you have lots of compression. But then you have a contradiction, right? Because air is actually faster when it's further apart and moving faster. So you just have to be careful with this. I'm not going to test you on this at all. The most important thing is that the wave speed changes per medium, right? So different things have different characteristics which sets their wave speed based on state of matter, temperature, and elasticity. All right, the last part of this is to use to calculate wave speed. Now, we can calculate wave speed the traditional way, which is through the wave equation. With the velocity equation, right? Distance over time. Disclaimer: I'm not going to include direction in any of my velocity calculations. We're just going to ignore direction. That's for another fun day. And we're going to talk about distance instead of displacement, since we're just going to talk about how far it went versus the direction too. So we're ignoring direction in all these calculations. So we can, this is a lab or demo I like to do too, is I take a slinky and I stretch it out and we watch the pulse go through and we calculate how long it takes to do that. It's a distance over time calculation, so it's pretty straightforward. The new thing I'm going to introduce is called the wave equation. Now the wave equation is nice because instead of like watching a wave and timing it, we can calculate the wave speed based on the characteristics or features of your wave. So if you notice here, I have frequency and wavelength. So wavelength is the size of the wave, and frequency is how often you make a wave. So if we have the size and the frequency, we can calculate the wave speed. And this is actually known as the wave equation. So I'm going to demonstrate these calculations. I'm going to go through these kind of fast because they're pretty straightforward calculations. In fact, you can probably stop the video at this point if you want. But to be thorough, I will go through these. So this is a fun exercise. Actually, before I go through these, once again, this poses challenges because you have two ways to calculate wave speed. So this is confusing. Another thing I want to point out to you, which is confusing, is the units of distance and wavelength are the same. That is confusing. So when it comes to solving questions, really what you're looking for is frequency. If you see something with the word frequency in it, it's going to be a wave speed equation. If you don't see frequency, then it's going to be the velocity equation. So just be aware of this. It's super confusing because of the V's are the same and the units for distances are the same. So look for frequency. That's going to tell you which equation you want to use. So this is a true story. One time I was watching, I got some tickets. It was actually Muse specifically at the TD Garden Arena in Boston, and I went to get tickets, and of course I was late doing that, and so I got the last seats. So I am literally the farthest away you can be. I was against the wall. This is not clearly drawn to scale, but you can imagine me. I'm sitting in my chair. I like Muse. I like listening to Muse. I'm very happy. Well, the silly thing about Muse was that is that I'm listening to the drummer, and this is, again, true story. Here's the drummer, my beautiful bass drum, right? He's got some cymbals here. Here we go. And he's like, I don't know. He doesn't have a mohawk, but I'm going to give him a mohawk. So I'm going to go ahead and throw some drumsticks on him. He's rocking out, yeah. So he's hitting the drum, and I actually see him hit the drum, and then I hear boom. So I see the drum, and then I hear the sound. I'm like, oh my gosh. I'm sitting so far away that there's a delay between the light wave and the sound wave. So I wanted to know, because that's who I am. I found the schematics of the TD Bank Arena, and found that it was roughly 250 meters away. And again, these are estimates, you know, they're not exact. But I do know that the speed of sound takes about 340, this is on average, meters per second. This is actually kind of low. It's actually a little higher, but again, we're generalizing here. And the question is, how long did it take for me to hear that sound wave? So, notice there's no frequency in this equation, so we're going to use the distance over time equation. The velocity is 340 meters per second. The distance, 250 meters over t. To solve this, it's going to be t is 250 meters divided by 340 seconds, meters per second, my bad. And then we're going to go ahead and calculate 250 divided by 340. We got 0.735 seconds. Took almost a second to get to me. That's pretty crazy if you think about it. So that's how long it took that wave to get to me right here. So fun fact. Okay, example number 2. So what is the speed of a radio wave? Whose frequency is that? So if you listen to the radio, you'll notice that you have the, the frequency, right? The 97.5 or 101.3 or 99.9. Those are all frequencies. And they're actually measured, they don't tell you, but they're measured in megahertz, where mega is to the 6th. So I actually converted it already. So this one has the word frequency in it, which means we're going to use the wave equation. So we know the frequency in megahertz. We got it into regular hertz. I like to listen to 104.1. That's the frequency. Times the wavelength, 2.88. Of a radio wave, they're pretty big. So, perfect. 2.99 times 10 to the 8th meters per second. So, a little big. And in fact, spoilers, this is a very special speed called the speed of light. This is, of course, generalized and simplified. It's actually about 3 if you do it. And we use the symbol c to represent the speed of light, but right now v is fine. So that's the velocity of the sound wave generated by radio waves. I'm going to show you this one because this one is not straightforward, and a lot of people have questions on this one, but I like it because it's not just plug and chug. You have to think about these numbers, right? So we have Noah formula, right? So he is hiking through a canyon. Here's Noah. And he gets to a canyon. So the canyon's very big. We're going to not make it to size. There we go. This is a canyon wall. So very big, solid structure there. Now, he decides to scream. I'm sure everyone's had a chance to do this, right? Yell at a wall. You hear an echo, right? That's him yelling. So the sound goes there. But then, to hear it, it has to come back, right? They're there in the back. In fact, Noah formula lets out a scream. An echo is heard 0.82 seconds after his scream. In other words, this time represents the time to go there and back. T is equal to 0.82 seconds. The question, though, is how far away is he? Now we know the speed of the wave, 342 meters per second. Now we're going to use the velocity equation to solve this, distance over time. But you have to be careful, because if I just use these numbers the way they are, I'm actually going to get the wrong answer, because that will calculate the distance from here to here. I hope you notice that's two distances. And what we want to know is just one distance, right? We want just how long it took, how far away it is, not how far away and back it takes. So you could do this a couple ways, but what I'm going to do is take the distance and divide it by 2 to just get the time to the wall. I don't want the time to the wall and back, just the time to the wall. So this is 0.41 seconds. Therefore, now I can solve it out with 342 meters per second is equal to d over 0.41 seconds. So if you're doing your mastering physics and you come across a similar question, see if you need to, there's some decimal places there, I guess I'll put them in. Need to double or divide by 2. That's one common mistake that people make. That's how far this canyon is, 140 meters from here to here, like that. So just careful with your numbers is the biggest take home from this. Most of them are plug and chug, but when they're not, you know, make sure you read the questions so you can determine when it's not entirely plug and chug. And just for fun, we'll do this last one. What's the wavelength of our sound with the frequency? So the word frequency is there, so we're going to go ahead and use this equation. 340 meters per second is the speed. 256 is middle C on the piano. So if you walked up to the piano and played the middle note, that's that frequency. So what's its wavelength? It's a pretty big wavelength. It's the size of me. 1 1/3 meter. That's a big wave. There you have it. And that's the wavelength. Okay, this is just a summary slide, as you can see, and another summary slide of all the equations and everything that we went over in this lecture. So I hope at the end of this lecture you have a little more understanding of the wave anatomy and some of the wave features that you will be calculating. You may have done a lab already that did a lot of these calculations, and if you haven't, this is where you're going to go with your lab in terms of doing your waves. And we're going to continue learning about waves in our next video called sound waves. Once again, this is like my favorite topic in the world, so I'll talk and do some demos with you. I'll do some demos even though there's no audience here and show you some cool things about how we hear and what we hear and why we hear what we hear. So that'll be our next video. All right, great. Thanks for joining me. Have a great day.